So today I'm going to talk about different methods of hypothesis testing, and I'm going to also give some examples on how to use Actable AI to do some of these hypothesis testing with different data sets. So the agenda of today is that first I'm going to remind about what is a p-value, and then I'm going to talk about the type 1 versus type 2 error in hypothesis testing. And what is the difference between the one-sided versus two-sided tests? And then I will go on to talk about parametric versus non-parametric tests, and then unpaired versus unpaired test. And then I will talk about Ttest, Anova, Chisquare Test, Mann Whitney, Wilcoxon test, Spearman correlation test, and we'll give some demo and example on how one can do that easily. So let me remind you of what p-value is. Right? So p-value simply is the probability or the chance of the observed effect to be at least as extreme under the null hypothesis. So when we assume that if there's no effect at all, then p-value is the probability that the effect can be as extreme as the observed values. Right. So here we can see the graph below. So assuming that we have the distribution, we have a sample and we have the mean, right? And we know that, for example, under the central limit theorem in the class 1 that we got, is that the sample mean has the distribution as a normal distribution, right? So under the null hypothesis, let's say assume we have the mean here. And then if we have the observed value, observed sample mean here, then p-values in a one-sided test is basically this yellow area, which is a probability of the sample mean to be at least as extreme as the observed values. So that is p-value. There are normal two types of error in a hypothesis. And in the situation where we have, for example, in the true value is that if there's no association, there's no effect at all. There's no effect at all, but we reject the null hypothesis, then that is a type 1 error. That's a type 1 error. Okay. And if in the case that there is actual effect, but after doing hypothesis testing, we fail to reject the null hypothesis, that is a type 2 error. That's type 2 error. So type 1 error is simply that there is no effect, but we say there's an effect. And type 2 error is when there is an effect, but we say there's no effect. So there's type 1 versus type 2 error. And one-sided test versus two-sided test. So here on the left-hand side, we have a kind of an asymmetric distribution. And in this asymmetric distribution, this kind of distribution is more appropriate to do a one-sided test. But if you have kind of a symmetric distribution, like this normal distribution, then you can apply a two-sided test. So the difference is that in the one-sided test, we don't really care about the effect in the opposite direction. So this one-sided test is less rigorous than the two-sided test when we test on both sides of the direction. So we're interested in if there is any difference on either side of the distribution. So one-sided test is less rigorous, and two-sided test are more rigorous, right? So that's why that one-sided test is more prone to one error. Why the two-sided test is more prone to the type 2 errors. So we can, to my opinion, we should apply the one-sided test only when only when the effect in the untested direction is negligible. For example, if you want to test a new drug and you are only interested in that whether that the new drug it has like worse effect than the old drug, then that might be fine. And I mean, if the new drug has a stronger effect, like better treatment outcome than the current drug, then it's a good thing and it can be negligible. It's not as important as we found out that if the new drug has worse treatment effect than the current drug. So that is when one can apply the one-sided test. Right? But normally I would choose for a two-sided test as much as possible. It's more rigorous, and it also depends on the trade-off between Type 2 and Type 1 errors. But basically the Type 1, the one-sided test should only be used only when the effect in the untested direction is negligible. And parametric versus non-parametric test. So here, if we know the distribution of the test statistics or the distribution of the data, if they have we know that distribution, or they have like a normal distribution like on the left here, then we can choose a parametric test. So the otherwise choose a non-parametric test. And also we should remember that like parametric test for the group means, while the non-parametric test for the median. That's for the median. So the difference, right? So when our data size or the sample size is large enough, like more than 30 as recommended, we know that the sample mean is always follows the normal distribution, then it's safe to just choose a parametric test. Also, otherwise, be careful when choose a parametric test. And why for non-parametric test, it requires the variance to be similar in different groups, similar variance. So it's a one requirement what to remember, otherwise that it might not give the wrong result, right? And the non-parametric tests usually have a higher Type 1 error than the parametric test. So it can reject the null hypothesis more often. Okay. So the difference between non-parametric tests and non-parametric tests. Here are some example of different parametric tests and non-parametric tests. So we have like a few tests here, like Ttest, Ttest, Ftest, or Oneway or Twoway Anova, Pearson correlation test, are parametric tests. And Wilcoxon test, Mann Whitney test, Chisquare test, Spearman test, and Spearman correlation test are non-parametric tests. Next, we'll talk about paired versus unpaired tests, and also one sample test. So one sample test is basically if we have one group of that we have the data from, and we know like the mean of the population. We know the mean of the population, and we survey, let's say, just one group of people. And then we have the distribution of these values and the mean of this survey sample. Then we can use the one sample test to compare the sample mean versus the population mean. So that's one sample test. Unpaired sample test. So if we have, we don't know the population mean, but we have two groups, and we survey two different groups independently, and we have the values of each of the groups, and we want to compare the mean between two groups, and we want to see whether there's a difference between two groups. Then it's when we choose for unpaired sample test. And the pair test is when we have just one group of say people here, and we have the we want to see the difference in different times, different points of in time, then we can use a pair sample test. So for example, if you have the same group of people, and then you measure a value before a treatment, and then you measure the same values after the treatment, and you want to see the difference between the values before treatment and after treatment for the same people, then we go for a pair sample test. Right? So there is one sample, unpaired samples, and pair sample test. So next, I'm going to talk about the student Ttest, or normally called Ttest. So this hypothesis testing is applicable when you have like the tested values are continuous, right? And we also have the sample means follows a normal distribution. So these two conditions, and it's not all, but these are most important conditions, and that the values have to be continuous, and then sample mean follows a normal distribution. And this second condition satisfies normally is when we know that if the population distribution is also a normal distribution, or we have a sample size large enough so it can satisfy a central limit theorem. So it's usually larger than 30. Okay, this is when we can apply a student Ttest. So let me show you an example of a case where I can do. We can use a one sample test. We can use a test with active YI. So it's worth knowing that that do all this kind of statistical inference and hypothesis testing is free on our platform, so anyone can use with any data set. So here I'm going to show a Ttest of from a UCI income data set. This is the survey, census survey from the census in the US. It surveyed people and asking for different information from demographics to information to their income, etc. So we have this data set, and we have information about the gender of the survey people, right? And also the the number of hours the work each person work per week. So here we want to test whether there is a difference between the number of hours, working hours per week between males versus then a Ttest and unpaired Ttest here, and unpaired Ttest. And here, what you need to do is just to choose unpaired Ttest in our analysis here, and then there's a different option where you can choose whether it's an unpaired Ttest or should be a paired Ttest or it's a one sample Ttest. Right? Here in this case, we have a unpaired Ttest because these two are completely different people. And then we have the test that we choose group by gender, sex, right? And then we choose a tested value as the number of working hours per week. And here I just go for a two-sided test, and then that's it. I click run, and then we will have the p-value here, and we also have a box plot of the distribution of the number of working hours per week for male versus female. So here where p-value is small, is almost equivalent to zero. So it definitely we can make a conclusion that there is a difference in the number of working hours between male versus females. So that is an example of a unpaired Ttest. Okay, next is Oneway Anova. So Oneway Anova is quite similar to Ttest, to unpaired Ttest, but we can use it for more than two groups. So previously we saw that student Ttest were applied to two groups of male versus female. But if we have more than two groups, then we can use like Oneway Anova. Then this test can tell us that if there is at least two groups, there's a difference in at least two groups. So here I'm going to show an example of the Oneway Anova, where you can test if like the hours per week are the same or different in different occupations. So again, we are looking at the same data set of the UCI income data set, and now we are looking at different occupations, different people with different occupations, and see whether there is a difference in the number of working hours between different occupations. Right? So again, what we need to do is just choose this ANOVA from the this analysis, and then you choose this data set, the UCI income data set, and then here we pick Oneway Anova, which is Oneway Anova here, right? And then what the outcome values, the tested value is the number of hours per week, and the occupation is different groups that we want to look. And then we click run, and then it will show first a box plot of the distribution of the number of working hours per week in different occupation groups, right? Different occupation group here we see, for example, in the executive managerial position, then we have the median of number of working hours about 40, right? 40. Meanwhile, in say in armed force or no, in private house service, then we see a median of about 35 hours a week. So here is a box plot of that distribution of number of working hours per week, and here we see the result, the ANOVA test. Right? Here we see the F score. F score is if F is close to 1, then say we usually see no difference. But here we say F is very large, and also this is the p-values. The p-value is almost 0 here, so we can make a conclusion that there is definitely there is a difference in at least two groups in among of these groups. At least two groups have different number of working hours per week. Number of working hours, and if you want to see which group have a different number of hours per week, then we can look at the Ttest results. This one, it will do a pairwise test for each pair of different occupation here, and then we see the p-value here. For example, when we look at here, we see that executive managerial and armed force actually have non-statistically significant difference. So we cannot really say that these two group of occupation have different number of working hours per week, right? So that is Oneway Anova. Next is the Twoway Anova. So similar to Oneway Anova, but if you have more than two independent variables, right? For example, if you not only just to look at the different groups of occupation, but you also want to look at genders and occupation combined, then you can use Twoway Anova, and then basically similar, but you can choose more than one groups, one independent variable. So here again, we choose the same data set. Here we choose different here we choose Twoway Anova here, right? And then in this treatment, we can choose up to two independent variables. Like here, I'm going to choose occupation and gender, right? And then we click run, and it will take some time to run the ANOVA. And here we see the same box plot as the previous one, but it's split into two groups here of gender male versus females, right? Yeah. And we can see in the result, we also see that the p-values and the f-score in each different group and also combined. And here we see the p-value is almost close to 0. So we can make a conclusion that there is at least two groups have different number of working hours per week. either occupation or genders. And then here we also look at the Tukey test, and we also again we'll see the pairwise test between different groups. So here, for example, we also see the difference between male versus female here. Right? Okay. So that is two-way Anova. Two-way Anova. Next is the chi-square test. So this is also one of the popular one. So this test is applicable when we have, say, we want to test the difference in the expected frequencies in one or more categories. So if we have, for example, if we have males and females, right, and each person have a different occupation, I want to see, say, the ratio between male versus female is same or different in different occupation. So the ratio of frequency is the same, then we would use a chi-square test. Chi-square test. So here, I'm going to show an example. Also in the same UCI income data set. So if we want to see whether the ratio of male versus female are the same as in different occupation, then we're going to choose chi-square test. Again, here you choose chi-square test, and then here choose group by occupation. I want to see the ratio of male versus female in different groups, and then you're going to pick section. Then just click run, and then if we run a chi-square test on this data set, and then it show here we have a bar chart to show the values, the number of males versus females. Males are orange and females are blue in different occupation, and then you see if whether these have the same ratio or different ratio. And basically here it's return the p-value, saying that there is definitely a difference in the ratio of male versus female in different occupation. Here we also see the contingency table, which is the frequency, the number of male versus females in different occupations. So that is chi-square test. So next I'm going to talk about Mann Whitney test. This is similar to independent t-test, but it's a non-parametric one, right? And it can be applicable to both continuous and ordinal data. So, for example, if you say if we look at the same data set and want to see if there's a difference in the number of education taken by male versus female, so we can use a Mann Whitney test. This is more appropriate than the t-test because the number of education taken is usually range from, like, say, 0 to 5, then mostly, and it's not normally distributed and not continuous, so it's more suitable to use Mann Whitney than the student t-test. So. So again, it's very similar to the student t-test. You need to do is just select the group, or different groups that you want to compare. Here we have the gender, and then we'll test the value number of education number, and we choose a two-sided test, and then click run, and you will see a box plot of the number of education taken by male versus female, and then we have the p-value here. Here we have the p-value is 0.257, which is quite large, and then we cannot reject null hypothesis, and we cannot make a conclusion that male versus female have a different number of education taken, right? So that is Mann Whitney Ttest. The next one, which corresponding to the parametric t-test, pair t-test, is the pair Wilcoxon test. So when you have, it's similar to this pair t-test, but it's non-parametric, right? And it's important to know that that's for the median, the difference in the median instead of the mean, not unlike the t-test. That's for the non-parametric, that's for the median, the difference is the median, right? So for example, You want to test if there's a difference between like the amount of time an autistic child is engaged in repetitive behaviors before and after treatment, but you don't have many data. You don't have too many data points. You have only a few children that you survey. Right? So you cannot really use a parametric test there. So here we need to choose for a non-parametric test. Here's an here we choose like Mann Whitney and Wilcoxon. Here I'm going to choose a Wilcoxon test here, and we choose the values before the treatment, value before the treatment, and after the treatment. I'm just going to swap two-sided test. Then I click on, and then you will see the same. It's a box plot for the amount of time that the children engage in repetitive behaviors before taking the drug and after taking the drug. And then we see the p-value is small, but not less than 0.05. So we cannot really reject the null hypothesis, which is that the drug doesn't have any effect in the number of hours the children, the autistic children, engaged in repetitive behavior. So again, that is pair Wilcoxon test. Another non-parametric test I don't want to mention is the Spearman correlation test. This one also was mentioned in the previous class. So basically, the test it is just to check whether there is an actual correlation between two variables, right? And they can be either ordinal or continuous. So here I'm going to check if there's a correlation between wine quality and alcohol level. Then we need to do it to just go to the y and then we choose correlational analysis. Here we have a correlational analysis. Just choose correlational analysis for this data set, and then we choose the correlation target is a y quality. The y quality, right? And this correlational analysis can find the correlation in many factors. So we can here we just choose all of the factors. So we want to see if the correlation with the y quality. Then we just select all of the column in the data set. And then we see that here we see alcohol. It actually has some pretty strong correlation with the y quality, and all of the correlation here, the shown correlation only show the correlation with the significant, statistically significant. So the has a p-value less than 0.05. So it's a very simple way to do a correlation test, and then to see which are the most correlated variable to the interested variable. All right. So that's it. That is the end of my class today. If you have a question, feel free to let me know on LinkedIn, and I take time to